Hello everyone, I hope you're doing well. We are going to now talk about differential equations, and I just wanted to start by giving you a bit of an introduction and some motivation on why these are important and exactly what they are. So first of all, what is a differential equation? Typically we just abbreviate it DE. And a differential equation is an equation that contains an unknown function, so some sort of quantity, and how it changes with respect to another quantity, so basically a derivative. Okay, and remember that, we're only talking about equations that are written with respect to one variable, but realistically, for real life, quantities depend on numerous variables. So typically a function has multiple variables in it. So a differential equation is basically an equation with a function and its derivatives. And rates of change are described as derivatives mathematically, so contains a function and its derivatives. Yes, the order of the highest derivative in a DE tells you an order of the DE. So for example, if you have an expression that has the second derivative in it, we would say that that's a second order DE. If we just have an expression that's written with respect to the first derivative, we would say that that's a first order DE. Okay, so acceleration, for an example, would be considered a second order differential equation because it's the second derivative of displacement. And DEs are standard mathematical tools to model real life phenomena. So how do you solve a differential equation? Well, it really depends on the type of differential equation, but in general, you basically need to find a function that satisfies the DE. So in other words, if you think you have a solution to a differential equation, it's going to be a function that when you sub it back into your differential equation and its derivative back into the differential equation, basically left-hand side will equal right-hand side. So that's what we mean by satisfies. So what types of differential equations are there? So there's something called ordinary differential equations, which is the kind that we'll be looking at. And these are equations where the function is of a single variable. There's also something called partial differential equations, and these are equations where that unknown function has multiple independent variables. So, and then that's abbreviated ODEs and PDEs. And these can either be linear or nonlinear. So linear meaning you have a linear term, degree 1. Nonlinear means that you have, squareds or cubes, things like that involved. But here we will be looking at ODEs of the following form. Okay, so they'll look like you have a dy dx, and then on the right-hand side you will have some sort of function of x and some sort of function of y. So this can include constants, by the way. So for example, if you have something just xy, f of x would be your x, and then your g of x would just be y. If you had, say, 2 times y, your g of x would be the y, and your f of x in this case would be a constant, it would be 1. Okay, so these functions here on the right-hand side can also be constants. Okay, and this is known as a separable DE. And why is it known as a separable DE? It's because you can split up your derivatives, so put it in differential form, and you can put everything that has y's on one side, and then everything that has x's on the other side. So doing that process of putting all the y's on one side, all the x's on the other side, this is known as using the method of separation of variables. And so what I mean by that is if we took this expression here and cross-multiplied, so bring the dx up to here, okay, so we would have dy is equal to our f of x, g of y, and then our dx. What I'm also going to do is divide by my g of y, so I can bring it over to this side. And now I have all of my x's on one side, my right, and all of my y's on the other side, on the left. And then what we do is we integrate both of these sides. So on the left side here, I have 1 over g of y dy is equal to f of x dx. So when we integrate on either side, when I write this, it means that here I'm going to be integrating with respect to y. So integrate with respect to y on our left-hand side. And then on the right-hand side, I have my differential x. So when I integrate, I'm integrating with respect to x. So integrate with respect to x on right-hand side. Okay, and for the plus constant part, we could go, plus c here, plus d here, and bring the c over to d, and then rename this to be a new constant. So typically what we do is we just go, plus c on the one side. And these types of differential equations are really useful even for the level that we're at and what we've learned, because they can be used to model growth and decay of populations. Okay, so let's just first look at a mathematical example where we can actually see how the math works, and then we'll talk a little bit more about the life science approach to it. Okay, so for this question, we want to find all solutions to this differential equation. It's a differential equation because I have some quantity A, and I have this quantity written as a rate of change with respect to x. So whenever we see A, it's almost like implicit differentiation. It's secretly going to be a function of x. So we're going to take this and we're going to do separation of variables. What does that mean? I'm going to cross multiply my dx. I'm going to divide by my A, and then I'll have all my a's on one side and then all of my x's on the other side. Okay, so we're going to go 1 over A on the left, and then I'll keep my dA here, and then I have 3, and then I cross multiply that dx. So you can think about it first like cross multiplying, bring this up here, and then dividing both sides by A. And the constant technically can go on either side. You can keep it down here, but then the integration's not quite as direct. So I typically, if I just have a constant, I keep it on the right-hand side. And now what we're going to do is we're going to take this expression, 1 over A dA is equal to 3 dx, and then I'm going to integrate both sides. Where on the left, I'm integrating it with respect to A, and on the right, I'm integrating it with respect to x. Okay, so the integral of 1 over A, well, remember, that's just a ln, absolute value of A. And then if I integrate 3 with respect to x, well, what function when I differentiate will give me 3? That's just going to be 3 times x. And then I'm just going to put plus c on the one side. Okay, and now what I want to do is I want to isolate for my a. I want to find out what that function is. Okay, so to isolate for my a, I have to get rid of this ln here. So I'm going to take everything to the e. So if I do that, I'm going to get e to the ln a is equal to e, 3x plus c. But remember that by properties of exponents, first of all, these two cancel, so we just have an a here. Okay, I'll talk about that a in 1 second. But this really means e to the 3x times e to the c. And e to the c, this just represents some number. It's just some constant. Okay, so typically what we do is we just rewrite this, we call it d. Okay, so this is just some constant. And the reason why I drop the absolute values is because e to the 3x, this is always going to be a positive number. So that's why I was allowed to do that. So as of right now, we can write our answer as a of x is equal to d e to the 3x. Now, when we say that this function or this quantity satisfies the dE, what does that mean? How can I check if my solution's right? Well, if we take this differential equation here and go d dx of both sides, okay, we're going to get dA dx on the left, and then I'm going to get d e to the 3x, and by chain rule, I'm going to have an extra times 3 there. But what is this? dE to the 3x. Well, that's what our a is. So this part right here is a, and so I get dA dx is equal to 3a. And this is exactly what I started with. Okay, so we say that this function satisfies our differential function, or differential equation, excuse me. And similar to when we first started talking about integration of indefinite integrals, if we are given an initial condition, okay, so let's say a at x is equal to 0, say it's just some number, I'm going to name it a naught. You would have an exact solution. An exact solution, a naught e to the 3x. Now, why is this the case? Where did I get this from? Well, this is my general differential equation. And if I plug in that initial condition, so a of x is equal to de to the power of 3x, and say I plug in 0 here, okay, so a of 0, I was told that the answer to this is a naught, and then e to the power of 0 is just 1. So I can solve for my d here. And this process of taking a differential equation and finding its exact solution, you have to have an initial condition. This is known as an initial value problem. Okay. Now, let's quickly talk about the generalization of this growth and decay model, now that you've seen a little bit about how the mathematics works. So say we have some differential equation, dp dt is equal to some constant times p. Okay, this is the basic model for exponential growth if this value for k here is a positive number, but if k is a negative number, then it would actually represent decay. And this is for some population p of t at time t. If given an initial condition, at say our starting time is equal to 0, say we have some population p naught, then the solution to the IVP is going to be p naught e to the power of kt. So if we have exponential growth, well, an exponential function, looks something like this, where I'm starting at the population p naught. Exponential decay, if I'm starting at the population for p naught, its graph would, look something like this. Population decay goes to 0. Okay, so that's the general problem for exponential growth and decay. There are also other models for population growth and decay, but this is the simplest one. Now, one thing that we talked about more so in the beginning of the term was we talked about the doubling time for problems. We're actually going to refer back to that here. So the constant k is related to something called the generation time or the doubling time. These terms are used interchangeably. In particular, if we can find a general expression relating the general population growth rate k and the doubling time t, we can do this by looking at our general solution for the IVP and solving it where we consider at the specific doubling time, we're doubling our population. Okay, so say we have this solution, and now I want to consider at a particular time, the doubling time, we get 2 times our population. Okay, so let's put this into our problem here. So let's consider p naught e to the k, but we'll put capital T. So we're looking at our population at time capital T. And I'm telling you that this is going to double that initial population. Okay, so p naught e to the kt. Well, p naught, these are non-zero values, right? So I can cancel them out. And then I'm going to be left with 2 kt. If I want, e to the kt. If I want to isolate for k or t for that matter, I would have to take this expression to the ln. So ln 2 is equal to kt. So this is the relationship between the generation or doubling time and our growth rate k. And notice that it doesn't depend on p naught. So intuitively you may think it would, but it turns out it doesn't. Now let's just look at an example of where, this could be useful for us. So say we have E. coli growing exponentially. So in other words, we have this sort of model where the initial time we have a certain population of E. coli. So we know that the solution has this general form. E of t is equal to E naught exponential e to the power of kt. So let's say the generation time is 40 minutes. What would the exponential growth rate be? So in other words, what we want to do is we want to solve for our k if we're comparing the generation time or the doubling time of the population. Okay, so for this particular problem, I'm told that the generation time or the doubling time is 40 minutes. So I can put that into my expression here to get k times 40. So isolating for my k, I get ln divided by 40. This is telling me that growth rate, which is approximately, if I actually plug this into a calculator, 0.01732 per minute. Now remember that typically we talk about growth rate in terms of a percentage. So if we multiply this by 100, we're going to get that the exponential growth rate is approximately 1.7% per minute. Okay? So hopefully that's a good little introduction to differential equations for you, and we'll talk more next time. Thank you.